So the topic for today is states of matter and how they are related to physical properties. So for those of you here in class, what are the states of matter that you can just come up with off the top of your head? Layton. Are they the ones that you named earlier? Maybe. What were the names that you named earlier? Liquid, solid, gas, and plasma. We'll talk about plasma in a minute. Those are the four basic states of matter. There are others. There are superfluids and non-Newtonian liquids and stuff like that, but we aren't going to talk about those. So the four basic states of matter are plasma, gas, liquid, and solid. Solid. Okay? And what's important for you to understand about these four is that I put them in an order, in the order of decreasing energy. Okay? So energy levels go up as we go up here, right? So high energy. Okay? So the energy is higher here in plasma than it is in liquid, and lower in solid than it is in gas. That is only for properties of the same element or compound. Okay? So if we have just a single compound and we change the energy, if we increase the energy, then it will move up this little list. Okay? If we increase the energy, it will move up the list here. It'll go from solid to liquid to gas to plasma. Okay? So we all know, we interact with gases and liquids and solids all the time, right? Gases we don't really think about a lot. Solids we think about a lot with just, stuff that we touch and feel, books and desks and the floor and so forth. Okay, but we don't think too much about gases, even though we are constantly breathing gases in and out. Plasma is something that I have never interacted with on a personal level, and I'm not talking about the plasma in your blood. Okay, plasma in your blood is a different thing. Plasma in your blood is essentially just water with some protein in it. Gases, liquids, solids. Miguel. So what is plasma? So we'll talk about what plasma is and compare it to the other states of matter. So don't worry, we'll get there. Okay? So gas, liquid, solid. Pretty straightforward. All right? Questions on any of that? Okay, so we're going to go on to the next frame here, and we are going to talk about solids. So for each of these states of matter, we're going to do a little drawing. Okay? Add image. One text box or laser. Sure. All right, so inside of a solid, so let's say that this is an object that we have here. Okay, and it is solid. Okay. And in this solid, we see the atoms. Okay? And the atoms are all arranged in a certain way. And this drawing is going to be beautiful. That's why it's taking me so long. We're just going to finish with this row. But you can assume that it will continue on through the rest, okay? So these red circles are particles. And what I mean by particles is atoms or molecules. Okay? What is the difference between atoms and molecules? You remember? Jay, don't remember? No? No, it's not that. It's not there. Okay. Remember that molecules are made out of atoms, right? A molecule is two or more atoms stuck together. Okay, but they behave very similarly. I'm just going to use the term particle though. Okay, and then we're going to do some using a different color. We use green. We're going to do connections between these particles. Wow, this is really pretty. Boop. So all of these particles are interacting with one another. They are bonded together in a pretty consistent structure, okay? So the green line means a bond or a strong interaction, okay? An interparticle interaction. Interparticle. We'll just do bond, okay? Interparticle bond. Okay? And then we're going to do another color here, and we're going to, let's do blue, as movement. But in a solid, the particles are moving, but they are not moving out of place. They're all stuck, okay? So they just kind of vibrating. So the blue line, or the blue, so the green lines are how they are bonded together, interparticle bonds. The blue is movement, okay? So that's the movement of the particles, okay? Movement, and that's not all that important for this state of matter, but you'll see how it becomes more important for the next states of matter. It's a little bit bigger. Okay, questions on how solids are arranged like that, and you could fill out the rest of this box using the same pattern. Okay. So the red particles are all connected by green interparticle bonds, and they are just vibrating. Okay, they're not moving anywhere, they're just vibrating. What, Lee? Vibrating. They're vibing, yeah. Okay? Questions on solids? This seems pretty straightforward, right? With liquids, what did you say, Lee? Yeah, this should be very similar to like 5th and 6th grade science, but we're going to get a lot more complex in just a little bit. Okay? Liquids. So again, we have our square of stuff here, and we're going to use the same things. We've got the red particles. We have the green intermolecular bonds or interparticle bonds, And then the blue is the movement. Okay, so just remember that. You should have that in your notes already, little guide. Okay, so in a liquid, we have particles. Whoa, that was not what I wanted to do. Where's my eraser? Okay. Let's try that again. We have these particles, and in a liquid, they're a little bit more random, but they're pretty close together. Okay. Whoa. And their bonds are kind of haphazard. Okay? So they'll bond together like that, and they'll bond together like that, and maybe like that, and you know, so they kind of bond a little bit, but they're not all bonded together in a nice, orderly fashion. And most importantly, while they are bonded together, they can move around. Okay? They're slipping past each other, moving around. And this movement, this freedom to move, is what causes liquids to flow. Okay? So we have particles that are bonded together, but only kind of for a short amount of time as they flow past each other. But they still stick. Okay? They still stick into one cohesive thing. Okay? Now that we've established a little bit of a pattern, what is our guess for what happens in gases? What was that, Franklin? Yes, they aren't connected by the green lines. Okay? They very rarely make interactions with one another, make bonds with one another, and they move around much more. So we have the particles here, and not only do they not make bonds very much, they spread out from each other. The reason why they spread out from each other is because they deflect off one another. They don't actually touch, but they deflect. Their electrons deflect each other. Okay? There are very few bonds, and it's more like a dotted line where they interact. Okay? It's more like a dotted line than an actual bond. They do interact, but they're not bonding together. And most importantly, they are moving around a lot more. Okay? And this movement is what spreads them out. Because they deflect off of each other. They don't want to be near each other. Okay? Questions on those? No? Does this make sense so far for everyone? Yeah. Yes? All right. So we have solids, liquids, gases, and then we have plasma. How could plasma be different from gas? Does anyone have any guesses? Miguel? It is hotter. Yes, that is a very important differentiation. It's hotter. Everything's what? In plasma, it'll be tightly packed together. Oh, no, no, you're good. In a plasma, we have a completely different situation. So we're going to make our square here again. In plasma, we actually don't have full particles. We have subatomic particles. We have broken particles. Okay? So the black is a broken particle. You think that I could draw a half circle? Have you seen my artistic ability on this? Yeah. So these broken particles have huge amount of energy. So our blue lines are very large. Probably not much bigger than the gases, but you get the idea. They have these particles have so much energy that they don't just break the interparticle bonds, they break the bonds inside of themselves. Okay? So plasma can be closer. It can be, but it doesn't have to be. Plasmas are extremely hot. And when I say extremely hot, we're talking millions of degrees. And it doesn't matter at that point if it's Fahrenheit or Celsius, it's just millions of degrees. Okay. Oh, there we go. But we're not going to deal with plasma, at least not in this class. The only time that you would ever be working with plasma is if you become a nuclear physicist specializing in fusion. It breaks the bonds inside of the particles. So for instance, if we took some, I don't know, oxygen, okay? So oxygen has, what, 8 protons? Is it number 8, right? Yeah, 5, 6, 7, yeah. Oxygen is element number 8, meaning it has 8 protons, and it usually has 8, sometimes it has 9 neutrons, okay? In a plasma, the electrons and the neutrons and the protons come apart, okay? They split away from each other. So it gets so hot that especially the electrons get stripped off and they just fly around by themselves. Okay?
Like gases, when you boil water and you make gas, you like break down.
Yeah, so when you boil water, it's an excellent question, Franklin. When you boil water, you're exactly right. You are breaking the bonds in between the water molecules. No. That would be a plasma. But so you're taking, so you know what a water molecule looks like, right? It's an oxygen with 2 hydrogens on it, right? All of those are kind of flowing past each other, moving around. When you boil that, they break away from each other. if you got it hot enough, you could get the oxygens to come off of the hydrogens, and then you would create a plasma.
Isn't that right? Like, contain that water with oxygen?
So you can make water into oxygen through something called electrolysis, and that is a different process. It takes quite a bit of energy, but not as much energy as making a plasma. Okay, good question. Yeah, breaking oxygen off of the hydrogen in electrolysis is a little bit different. Good question though. Okay, so those are the four basic states of matter. Now what I want to talk to you all about is the relationship between states of matter and, we all know temperature, but we need to talk about pressure. Okay? We need to talk about pressure. So if we look up something like this is called a phase chart. Pull it up for you. This is called a phase chart, right? And this, on the y-axis we have pressure, on the x-axis we have temperature. Here we have the gas phase. Anything in this sector of the graph will be in a gas phase. So let's say we're talking about let's just talk about water, okay? That's something that we are all familiar with, all three states, okay? Let's talk about water, good old dihydrogen monoxide, H2O. On a nice day, let's say it's 25 degrees Celsius outside, okay? So 25 degrees Celsius outside, right here, there's no numbers here, but let's just say it's right here, okay? 25 degrees C, and let's say we have 1 atmosphere of pressure, which is normal pressure here on Earth, okay? Normal pressure at sea level. So it's right here, it's the liquid phase, okay? We're all familiar with that, right? It's liquid water, okay? Well, if we decrease the temperature but keep the same pressure, we move left. And we decrease it enough to where it's -4 degrees Celsius, and now we're here. Okay, we're now in the solid phase of water. That's something that we're all familiar with, right? Solid phase of water, okay? Now it warms back up, and we're back at 25 degrees C. Well, what happens is you bring this water into a vacuum chamber, okay? And it's 25 degrees Celsius inside the vacuum chamber, but then you start pumping the air out of this vacuum chamber. And so the pressure goes down. So we move down on our chart, okay? Remember that it's still 25 degrees, but the water starts to boil. Okay, right around the time we hit maybe half of an atmosphere or like 0.4 atmospheres, okay? And the water starts to boil, but it's 25 degrees Celsius, which is just a little bit warmer than room temperature. In here, it's probably 22-ish, 21, 22 degrees Celsius. Does it feel like it's boiling in here? Do you feel like you could boil water in here? No, you couldn't, but if we pulled the air out of this room, water would start to boil. If the water started to boil, then your blood would start to boil, which would be a problem. Your blood would actually start to boil first because the blood in your body is warmer than the water in the 25 degrees Celsius. Okay. Now let's imagine we decide to go visit Mars as a class. Okay. So we go to Mars. And on Mars, it's a little bit cold. And when I say it's a little bit cold, I mean it's really cold. Like when it's a warm day on Mars, it's like negative 50 degrees Celsius. Mars is red, but that doesn't mean that it's warm. No, Venus is the warm one. Venus is 600 degrees Celsius, hot enough to melt lead. So that's fine. Okay, so let's talk about the fact that on the surface of Mars, it's negative 50 degrees. So we're here on temperature, okay? We're here on temperature, where my little magnifying glass is. But the pressure is insanely low, okay? It's really, really low. It's about 0.01 atmospheres, about 1% the amount of pressure that we experience here on Earth. So it's all the way down here, okay? Even though it is negative 50 degrees outside, it is enough for the water to be in a gas phase. So let's say we all go as a class and we've spent a couple of weeks in this spacecraft and we all start getting really sick of Robbie. Okay, just as an example. Okay, we all start getting sick of Robbie, just as an example. And we decide to vote him off of the spacecraft.
Vote him off?
No. Let me rephrase that. Sorry. Sorry, let me rephrase that. I used the word vote. Mr. Croshaw decided, because this is a Crowshocracy, that we are going to remove a person from our colony. What? I don't know. Let's just say he deserved it. Okay, so we throw him out of the spacecraft. No.
Makes sense.
What?
Makes sense.
And so here's what's going to happen. Okay, because it's so cold, portions of your body. Let's just assume that it's you. Okay, I just want you to imagine you doing this because it makes it a little bit more personal. And you are so cold, portions of your body want to freeze, but the water inside of your veins, even though it's getting very cold, wants to boil away because it's in the gas phase of this phase chart. Okay, because the pressure is so low, even though the temperature is really low, it wants to boil away. Frankie. Atmosphere, yes. So the atmosphere here on Earth keeps us from freezing and boiling at the same time. Yeah, kind of. That's more the magnetosphere, but yeah. So the triple point right here, that's an excellent question, Miguel. The triple point is where this, whatever compound this is, we're going to just assume that it's water, is trying to be in all three phases at the same time. Okay? For water, I think that it's like negative 12 or something like that degrees Celsius, and then it's at a really low pressure as well. You can just look it up. Triple point. Water triple point is point. Oh wait, see, it's here. Oh, let's see here. Where's the triple point? Solid, liquid, water, vapor. Okay, so it's 0.01 Celsius at 611 pascals. Okay, this is what it looks like when it's at the triple point. It wants to boil, melt, and freeze all at the same time. Cool. Nothing. It'll just be cold, but that's really low pressure. You don't want to deal with the pressure. No, because portions of it will freeze, portions of it will melt, and portions of it will boil. And portions of it will do something what we call sublimate. Okay?
So if it's not really lucky, you could live for like 5 minutes.
I don't know if you could live at that, because the problem is that the water inside your body is at body temperature.
But what if it so like the blood, it liquefied right before it went to your brain or like your heart, and like the rest it hurts and damages the lungs. Stay alive.
I don't know how humans would do it, the triple point. That's an excellent question. I really don't know. Okay, but so you know carbon dioxide, solid carbon dioxide, right? Dry ice. Y'all seen that before? Solid carbon dioxide. Dry ice for carbon dioxide is like here. Okay, it's here. But as the temperature increases, it does what we call sublimation. It goes straight from a solid to a gas. It does not melt and then boil. It goes straight from solid to gas. That's sublimation. Okay? And you can get water to do that as well, given the right temperature and pressure conditions. Okay? Do we see how temperature and pressure are related to each other when it has to do with phases of matter? Okay. So, oh, that's not what I wanted to do. Where'd my, what's up? Yes.
You know how they Titans like steam?
Yes.
How does that work?
That could be sublimation. Yeah, that could be sublimation. If you see, so sometimes ice will sublimate, or sometimes people call it sublime. But it's just in really low quantities. But if you've ever seen ice kind of, you can see vapor coming off of ice. But not vapor as in condensation, but vapor that is like, it's sublimating. Sometimes you can see that. It doesn't have to be at the exact right temperature and pressure. Sometimes it just, a few of the molecules get enough energy to just jump off of the ice. Okay, that'll happen. Yeah, and they'll go pew. Yep. Franklin, question?
If you like inhale it that and have a flavor.
Could you inhale? Yeah, I mean it's just water vapor. You can inhale water vapor all you want, man.
But cold.
Like go, but cold, yeah.
So
It would be cold water vapor.
so you can do like sublimate Coca-Cola.
So Coca-Cola is a little bit of a different situation because Coca-Cola is a solution. It's just water with stuff in it. I don't know if you can sublimate Coca-Cola. Is it worth trying? Sure. You could sublimate the water in Coca-Cola, but I don't know if it would bring any of the sugars with it. Yeah, Jay? Yeah, so the triple point is where the material wants to be liquid, solid, and gas all at the same time. Okay? So here's what I want you to put down in your notes. Okay? We'll put this as black. Temperature and pressure are the controlling factors of what state of matter a compound inhabits. And I'm going to make this larger. Whoop. Okay. Temperature and pressure are the controlling factors of what state of matter a compound inhabits. Okay. So the lower the pressure, the more a compound will want to be a gas. And the higher the temperature is the same thing. Higher the temperature, the more the compound will want to be a gas. Okay? So lower pressure, higher temperature, it wants to move it toward the gas phase. All right? We're going to look at that, the phase chart one more time and talk about kind of an interesting situation that we encounter here on Earth. Okay? Yes, you can heat up a room by pressurizing it. So the higher the pressure, the more the temperature, the temperature will go up. What's up? Will want to be a gas. Higher the temperature and lower the pressure. Okay, so let's talk about something at a really high temperature. Okay, let's say we're talking about water again, because this is the thing that we understand the most. Water boils at what temperature? 100 C. Okay, 100 degrees Celsius. So 0 to 100. Yeah, Celsius is actually based on a real physical phenomenon. Not just how I feel. Fahrenheit is the most like emo way of measure. Yeah, because like, listen, how I feel about this, okay? How I feel about this is it's really hot. Imagine. So, okay. So generally, water boils. So we say water boils at 100 degrees Celsius, right? Well, it depends. Okay. Here in Ogden, Utah, water boils actually at about 98 degrees Celsius. For real. Okay. Depends on the day. Depends on the day. But because we live at a higher elevation, we have less air pressure. And therefore, our evaporation point is just slightly lower here. Okay? Whereas at sea level, it boils at 100 degrees Celsius. Okay? But down at the bottom of the ocean, there are these ocean floor thermal vents. Okay? Geothermal vents. It's superheated water coming out of essentially a volcano. Okay? And we're talking about water that is 150, 170 degrees Celsius. It's hot, okay? But it's not boiling because the pressure, right? So look, the temperature is really high, but so is the pressure. So here, we're still in a liquid, even though it's really hot water. We're still in a liquid, and because it's still hot, because it is still liquid, even though it's really, really hot, things can live there, and they do. Things live in this water, even though it's insanely hot. You and I couldn't live in there. But things can live there because the water is not boiling. Miguel and then Jay.
What is critical point?
The critical point is when you start to get plasmas. Yeah. Critical point is when you start to get plasma. Franklin?
Aren't there like air bubbles boiling?
There are small air bubbles, but it's not full on boiling, okay? The reason why boiling is not good for you is because it destroys the proteins in your skin and in your organs. It destroys all the very delicate chemicals in our bodies. That's the same thing with freezing. It's not good for us, okay? Well, just a second. Jay? Uh-huh. Yeah, so down at these geothermal vents, there's all sorts of really cool things. There's these tube worms. There's also the Yeti crab, like that white, that looks like it's furry crab. Okay, fine, I'll show you. Yeah, it uses its little hair-like structures to catch bacteria that it feeds on. Yep. Yeti crab, not Yeti. Yeti crab.
I've seen like 50 different episodes of wild crabs, and it's just them trying to find treasure.
Yep, here we go.
Ooh, I found a
Tasty.
I don't know, it might not taste very good. Maybe it does. But yeah, these things live in water that's like 150, 170, 200 degrees Celsius.
and wear long sleeve shirts.
And they're wearing, that's what's funny, like they're not wearing like a sweater. They're just wearing arm warmers, like fuzzy wool arm warmers. Bring those into fashion. Okay. Questions on any of this? Pretty straightforward? Okay. This is where I'm going to end the recording. Yeah, like and subscribe. Okay.